In this video, I'd like to work through this example from class, and I'll try to do so in one take rather than pausing for explanations as I did during class today. So hopefully you recall that we're dealing with an airplane that is flying 500 miles per hour and it's headed due south. The jet stream is the wind that's pushing at 80 miles an hour in a northeasterly direction. Now, due south, we noted, is 270 degrees on our 360-degree scale, and northeasterly direction, that's perfectly northeast, that's halfway between 0 and 90, so we'll call that one 45 degrees on our 30-degree scale. So in part A, we need to identify the rectangular coordinates of this polar coordinate pair. And we can do so with this format that we had mentioned earlier. The vector, we'll call this one v, its magnitude times cosine of the provided angle measure and sine of the provided angle measure will produce the vector component in the x direction and the vector component in the y direction. And we said that the x direction component is our I component in ij notation, and this value is our j component. So when we're talking about ij notation, that would be just the numerical values that we obtain in this vector result. So for the velocity of the airplane, they're using the subscript a in this case. We need the magnitude of the airplane, and we need the angle measure of the airplane. So I'm going to use theta A and theta A again. So theta A for the angle of the airplane. So in this case, we're dealing with 500 miles per hour as our magnitude, and cosine 270 and sine 270. Now, without a calculator, you should be able to determine that cosine of 270 is 0 and sine of 270 is -1. Those are results that came right off of our unit circle. And we also know that scalar values multiply into vectors, so we end up with a vector result of 0, -500. And if we were to write that in true ij notation, as they're asking for here, we would say 0i minus 500j. For our airplane. And the computations for the wind vector are done essentially the same, but you'll notice that if we evaluate cosine of 45 and sine of 45 without a calculator, we get these radicals with fractions. And when we multiply or distribute the 80 magnitude into the vector, we get 40 times the square root of 2, which is okay, again, if we don't have a calculator, but if we do have a calculator and we want a decimal result, we would find the result of 56.5685, so 56.5685 in each direction. So if we were going to report this one in ij notation as requested, we would say 56.5685i plus 56.5685j, or as a precise solution without decimals, 40 root 2i plus 40 root 2j. So depending on what the instructions are asking for, we would provide either of those. I'm okay with either if you complete this work on paper for me on a test or a quiz, as long as you show your work along the way. Now, what we would like to emphasize for part B and C is that the airplane's vector and the wind vector will combine to create a resultant vector. And this resultant vector is what's going to be used to help us find B, the velocity of the 737 relative to the ground, and the direction of the 737 relative to the ground. So when we're answering part B, I think the solution that they want is actually the result in this component vector form in ij notation still, even though they're not real clear about that. So I would show this here because, again, the velocity, I guess I should mention this, velocity again is the description of the vector whereas speed and direction are the magnitude and direction, so the components of the vector. So velocity, this is our clue that we want the result in vector form. And so we might say something like this: the vector or velocity of the airplane relative to the ground is this red vector, is the sum of the velocity vector of the airplane pushing itself plus the velocity vector of the wind affecting the airplane as well. And so we just noted that the rectangular components of the airplane were obtained. That's 0 and negative 500. And we also have the rectangular components of the wind vector. We'll call that 40 root 2 and 40 root 2 for precision. And so now we can sum these two components together, and we have 40 root 2 for the horizontal component, and whatever the result of 40 root 2 minus 500 or negative 500 plus 40 root 2 is. Now, again, I'm showing this because these are precise answers, and we were able to complete them without the use of a calculator. If I do reach for a calculator and compute these results, well, here again, 40 root 2 is just 56.5685. And negative 500 plus 40 root 2 comes out to be negative 443.4315. And that would be a good result for this vector. We could also, of course, label this in IJ notation as, well, let's go ahead and show it in our exact form this time. In IJ notation, I might write this as 40 root 2I plus, and since I can get a precise result by the sum of these two, I would write negative 500 plus 40 root 2, the quantity of that in the grouping symbol, times j. So there's an interesting way to report our vector using IJ notation. Again, I'm still a fan of this component notation using the matrix, but I understand that MathXL might ask for results in this form too, so we better be prepared for that. Now I've extended my page a little bit to fit Part C in here. You may want to add this to another sheet of paper if you don't have enough room. But Part C is finally asking us to find the actual speed and direction of the 737 relative to the ground. So again, speed, we're talking about the magnitude, so the length of the arrow, and direction, of course, would be the angle measure of the final arrow. And so we've got to be a little bit careful here, or at least be prepared for unusual results. When we calculate the angle measure for the direction of this arrow, we're expecting a result somewhere between 270 and 360 degrees because this arrow does land in the fourth quadrant. Unfortunately, however, the results from our calculators may not show that. Calculators are programmed only to give one result to a trigonometric equation, and you may recall from our notes last week that there are often two results for most trigonometric equations inside the unit circle. So if we get a strange result off the calculator, we will have to be prepared for that. Now, the length of the vector is actually quite easy to compute. This one's pretty straightforward because we now know the horizontal component and the vertical component. The 40 root 2 is our horizontal component of this vector, and this negative 500, or let's call it the negative 443 right now, that's our vertical component. And with right triangle trigonometry, we've got an opposite and an adjacent side, so tangent or cotangent would be appropriate along with our Pythagorean equation to solve for the pieces that we need. But again, let's go after the diagonal first, the length of the hypotenuse. Well, that would be the vector's magnitude, so I'll talk about the velocity of the airplane relative to the ground, so the velocity against the ground. The magnitude symbol is equal to the square root of 40 root 2 squared plus negative 500 times the, plus 40 times the square root of 2, that quantity squared. Now, I think reaching for a calculator here would be appropriate. There's not a whole lot we can do to simplify this expression. There are some things that we can do to cancel out some of these squares and square roots, but honestly, this is definitely going to be a calculator component. And so when I reach for the calculator, I try to enter the values in the calculator exactly as we have them written on paper, because I'm pretty confident in how that setup looked. So when I press Control Enter here, the result that I get is the length of the diagonal of that final vector. So we've got 447.0251, and this is a measurement of speed, 447 miles per hour. It's not really a vector yet because we don't have the direction, but that's easy to obtain. The theta value is equal to either the tangent inverse of the opposite divided by the adjacent, so the y component divided by our x component, or we could say the cotangent of the x component divided by the y component, because that would be adjacent divided by opposite. Oops, I should use inverse symbol here. Now, I'm a big fan of the cotangent here because our horizontal component is on top of the fraction, while our vertical component is on the bottom of the fraction. And if you think of the format of our vectors that we've been drawing so far, again, we've got our vertical component on the top with our horizontal component on the top with our vertical component on the bottom, just like the cotangent setup would be. If you end up using tangent inverse, I should say, the values are going to be the opposite direction of the way all of our vectors have been written. Shouldn't really change our mathematical results, but for consistency's sake, I tend to use cotangent. So let's see what we get here. For tangent inverse, our vertical component, I'm going to switch to the decimal values here, negative 443.4315 divided by 56.5685 should be the same as cotangent inverse of 56.5685 divided by negative 443.4315. So again, if I wasn't real clear before, you can notice now how this cotangent computation is set up just like the vector that we established here in this step, whereas the tangent inverse setup utilizes the same numbers just in a different order. Now from the calculator, let's see what we get. So this is pretty interesting. When I use tangent with the values that I prescribed, we get an angle measure of negative 82.73. So negative 82.7301 degrees. But for cotangent, we get 97.2699 degrees. Now, clearly those two numbers are different, and if we think of a unit circle, they're also pointing in different positions as well. So what gives? Which one's the right answer? Well, as they sit right now, I would say neither of them are. Here's negative 82 degrees. That's a value below the x-axis. I don't like negative 82 degrees because it's not a number inside of our unit circle. And then the problem we have with 97 degrees is that it's pointing in the wrong direction. I think reproducing the answer from the tangent result is pretty easy to do. We can just add 360 degrees and get an acceptable result. 277, let's clarify that here, 277.2699 degrees, and I think that would be perfectly acceptable. But I was saying earlier that I like cotangent because of the format. However, we do have to be a little bit careful here. You'll notice that there is a negative sign written in the denominator, and the same result from our calculator would have been obtained if we put the negative sign in the numerator, negative 56.5685 over positive 443, I should say, 443.4315. The location of this negative symbol does not matter, but it does change the physical results. Here, we are indicating a horizontal movement of positive 56 and a vertical movement of negative 400. So the result that we expected to see would have been to the right and down from our origin, and so we would have hoped to see a result that points in this direction. However, what the calculator interpreted this as, and this is just a programming issue with this machine, a lot of calculators do this, they interpreted the negative sign, or calculated the result, as if the negative sign were in the top. And so in the top here, they're talking about a movement of leftward 56, but upward 443. So that's where this result came from. Now, this happens surprisingly frequently. The calculators produce results in a direction that we may not expect them to be. However, what's fortunate for us is that the correction is very easy. In this particular case, the calculated result was 97 degrees. This vector arrow was pointing exactly in the opposite direction of what we'd expect. So if we add to the calculated result 180, and we don't always do this, and this is the tricky part. We don't always have to add the 180, but in this case, clearly our result was wrong, so we can fix that by adjusting. Our setup was good, but the calculated result was not what we expected. And if you haven't already guessed, or if you haven't already done the math, you'll see that 97.2699 added with 180 is precisely 277.2699. And that result should look awfully familiar to you. It's the same result we obtained just a moment ago. And so I want to emphasize here that in either case, the tangent or the cotangent result off of the calculator screen did not give us the answer that we were after. In both cases, we had to manipulate the result to obtain the correct answer that we're going for. What makes this even more challenging, beyond just the one correction, is that sometimes in Math Excel they ask for an answer that's even different than this, and they use the bearing notation that we had mentioned at the start of this, actually start of last unit. And the direction that we've established here, this 277 degree angle, is actually 7.26 degrees east of south. And so if we were going to report this on Math Excel and they are indicating for a bearing notation, we might report south 7.2699 degrees east. So lots of different ways to report these angles. There's no set in stone method that works every single time. This is where your understanding of the trigonometry and the unit circle will definitely come into play. You can interpret the calculator's results and report the answers in any form that the instructions require. So I hope that helps. I know in class we were a little bit distracted and sidetracked with our conversation, but again, this was meant to clarify all of that. And of course, you can jump around as needed if that would help you in this video. Thanks for watching.